I think we're in pretty good shape. We covered mass balance. There's two other big deals here in well, I guess three. There's three other big deals in Chapter 2, and I'd love to try to hit on all of them today. So the first three things that are coming right at me are chemical mass balance, and that is actually sort of keeping track of individual atoms.
Stoichiometry.
Stoichiometry, yep, and that's 2.3. Stoichiometry.
It's from alcohol fuels.
Yeah, that's
The other one is molarity, and that's 2.4. Another way to think of that is just concentration. Concentration. Not focusing your mind, but how much of something there is and something else.
Based on molar weights, then?
Based on molar weights, exactly. And then the next one is energy.
We're kind of play with the carbon baggies.
Yeah, I like that one. We could do the carbon baggies. Energy balance. And that's 2.8. So what I'm hoping to do, and I think what I can do in the next, we got 35 minutes left. I think in the next 20 minutes I can cover chemical mass balance. Now that we've got just regular old mass balance behind us, and molarity. So I'll spend about 10 minutes on each of those, hit the pause button, and then hopefully come back to energy balance. So chemical mass balance, let's bop right out to the dynamic periodic table. And most of what we're going to be dealing with in bioenergy, I might have said this already, but is hydrogen, carbon, nitrogen, oxygen. That's most of it. A little bit of sulfur, a little bit of phosphorus. But beyond that, those are our kind of go-to elements for bioenergy. So let's just dig right into
bright green ones.
yeah, this, you can think of the green ones as sort of life or whatever, yeah. So equation 2.3, let's write that guy down, see if we can't dig into it a little bit. Equation 2.3 is CH4 plus 2O2 becomes CO2 plus 2H2O. So, looking at this, I'm just going to go ahead and draw this thing out. And, hopefully you guys know that this is just methane. It's natural gas. And even yesterday at the Mansfield Center in Butte, they had right next to it, there were 3 stacks. I wish I had a photo of it. 3 stacks where they've got 3 gas-fired turbines. Pretty new. Used to be illegal to burn natural gas for energy. Now, we're fracking, it's there, and we don't burn oil for electricity. I mean, once in a while you'll see that, but it's like, no, if you're going to make electricity, you're going to burn coal. But now, with all the fracking, et cetera, it's sort of easier, cheaper to get a gas-fired turbine up and running. You can sort of turn it on, turn it off. Can't do that so much with a coal-fired power plant. But anyway, that's your natural gas. I was standing right next to 3 of them in Butte yesterday.
How much power were they turning out?
I don't know. If I had to guess, though, I would guess each one's probably on the between 1 and 5 megawatts, and they're for peaking energy. When everybody comes home, flicks on all their lights, or whatever. You've got a snowstorm, and all the electric heaters and whatnot come on.
What kind of gas pipe is it? 3-inch pipes or something?
My buddy Craig Thomas was looking for it. I'm gonna guess it's probably a 4-inch pipe coming in because we're trying to figure out if we're gonna do a biomass plant on that site.
Okay.
Where do you store the logs? Where do you grind the chips? There was a pretty sweet 200 horsepower electric motor sitting right there. I'm like, you could do some grinding with that. So.
That's interesting.
Yeah. Or what's this? Well, this is just oxygen straight from the air, which is pretty remarkable. I would love to know a little bit better. And one thing I like thinking about is like how old the oxygen molecules in the air are. Like some of them were just made, yesterday. Well, maybe not yesterday because I don't think there's a whole lot of photosynthesis going on. But maybe, if you've got a plant in your house, you could be breathing some very recently manufactured oxygen. Some of the oxygen molecules in the air might be, hundreds of millions of years old. They might have been, breathed out by a cyanobacteria and just never got breathed in. Just floated around. So, but that's your oxygen in the atmosphere. Here's your CO2, obviously, which is a combustion product of biology. We're making it right now. It's also a combustion product of technology. So it fits pretty well with both. And then and that's just water. Same thing. That's water's coming out your tailpipe. Water's coming out my mouth right now as I speak as a combustion byproduct of my own metabolism.
So is that pure oxygen then? Because air has different stuff in it.
Right. Good. Yeah. So good question. Is it pure oxygen? Well, what I could do, I could just put in. I could put N2 in this equation too. That's nitrogen because we know that the air is 80% nitrogen. All I have to do though is put it over here on the other side.
Oh, okay.
N2.
So it's irrelevant. Really.
Right. Exactly. It's not really. And so you could put it in your mass balance. And in fact, if you were running your gas turbine plant, in fact, it's kind of weird. The Mansfield Center had a nitrogen production facility. There was a big old slab, bunch of concrete. I think they took kind of gutted some of the equipment. But to make liquid nitrogen, really all you do is compress air. You just compress. And same thing with liquid oxygen. You just keep compressing air to the point that it liquefies. There's nowhere else for it to go. It becomes liquid. And I believe the nitrogen is more dense than the oxygen, and that it condenses at a higher temperature. So the nitrogen liquefies, and you just tap it off the bottom of the tank. The oxygen is still there. You keep squishing it. Once it liquefies, you suck it off the top. In fact, talk to these guys at Norco. Yep, there's a big air squisher, and turns into liquid, and you ship it around. So, good question though. So the nitrogen could be part of your mass balance, but it's not really taking part in the chemistry.
Right.
Okay. And under normal conditions, the methane and the oxygen wouldn't do anything. You have to get them hot. You have to add some spark, and that's why the gas turbines work, heat engines. Okay. Now the other thing to keep track of, again, I love to draw the little pictures. Here's your 4 hydrogens hanging off of your carbon, and that's more or less what a methane molecule looks like. Same thing with oxygen. Here's your O2, and I've drawn so what I do want you to be aware of is the lines in between each of these actually have a meaning. Carbon, let's go back to our periodic table. Carbon is sitting right here. I'm going to go up to the orbitals, and if you look really carefully, and maybe if I make this a little bit bigger, Control Shift Plus. If you look carefully, right here at the 2p orbital. So as I click here, you can see these little dumbbells show up. So there's kind of the X, the one that's back and forth. This one's right and left. This one's sort of up and down. Those are your 3 different directions. So these 3 orbitals, they're called the p orbitals. I can't remember what p stands for. but they kind of look like dumbbells. And you'll notice that in carbon, there's a missing arrow here, there's a missing arrow here, and there are 2 missing arrows there. There are 4 missing arrows. Each one of those arrows is just an electron. Carbon has 6 protons in its nucleus and 6 electrons circling it. Carbon would, quote, like to be neon. It would like to have 10 electrons around it for a low atomic energy state. It doesn't. Where's it going to get those 4 electrons from? Well, let's go up to hydrogen. It's simple. It's just a sphere with 1 single electron in its 1s orbital. So where's the carbon get those extra electrons from? From hydrogen. Hydrogen comes along, here's my electron, but now the these 2 atoms, or I guess in this case 5 atoms, 2 different species of atoms, are sort of locked together, sharing those 4 electrons. You set the thing on fire, you bring in oxygen. Where the heck's oxygen? Right over here. Oxygen, if you'll notice, has an electron missing there, an electron missing there. Where's it going to get them from? Just another oxygen. Well, in this case, in this case, just the other oxygen. So, mama oxygen's got, you can think of it in 2 different ways. Either 2 to share, or it's missing 2. So it can get up to that neon, right? Because if you look at neon, it's full. 2 in the 1s, 2 in the 2s, 2, and then the full 6 in the 2p. Then marching down, fluorine's missing 1, oxygen's either, you can think of it 2 ways, either missing those 2, or it's got the 2 extra. And that's and that's why I've drawn this, whoops, like so. Those are the 2 oxygen bonds. Okay, so on the left side of the equation, I've got 1 carbon, 4 hydrogens, and I've got 2 oxygens. So to come over here now, again, I know that 1 carbon has to be somewhere. Well, where is it? Right here. And it is now bound with the oxygen and its 2 bonds. That's just carbon dioxide molecule. So the oxygen still has 2 lines coming out of it, and the carbon still has 4 lines coming out of it. Each one of those lines just represents those electrons we were just looking at. Plus H2O. So where's that oxygen? It's right here. Where's the hydrogen? Right there. Right there. So now, very nice and tidily, the oxygen still has its 2 lines, and the hydrogen has its 2. Well, if you look over here, you say, well, gosh, what happened to well, in fact, what I neglected to do is draw that other oxygen on the left side. So there were a pair of these guys. There's 1 oxygen molecule there, another oxygen molecule there. Over comes the carbon. There was only 1 carbon on the left, so there's only 1 carbon on the right. Now I've got 2 oxygens on the left so far. Here's a 3rd. I need a 4th. And I need 2 more hydrogens. So there it is. So I've done a chemical mass balance of methane combustion. Everything, everything that came in on the right, came in on the left, is accounted for on the right. I didn't mess around with the nitrogen because it's not interact. If you get hot enough, and that's where the NOx come in, if you get too hot, you're making NOx, another greenhouse gas, not a good thing, but anyway.
Oh.
Yeah.
Okay, never mind.
Yeah.
They're sharing their bonds here, but here they're splitting it up between the hydrogens.
Yeah, that's right. I mean, that hydrogen's still looking for somebody to be associated with, and those 4 oxygens, 2 of them went with the carbon, and the other 2 went with the hydrogen.
Yeah, I was confused because there wasn't 2 lines on each of these oxygens.
Oh, right. Well,
It's
yeah,
just written different.
that's right. Yeah, it just happens. You're right. The 2 lines coming out one side to hang out with the carbon, and here one's coming out the left, and the other one's coming out the right to hang out with the hydrogen. So yeah, here we go. Nice. So that's chemical mass balance. think we're on track. Let's do molarity, 2.4. So this was all 2.3 right here. 2.3 chemical mass balance. Okay, so now 2.4 is concentration. 2.4 molarity. All right, so I'm just going to write the equation as I see it here. So N equals M, little m, over big M. Okay. The number of so I'm not going to, I'll teach it right straight from the way the book does it, so I'm not contradicting the book in any way. So the number of kilomoles of a substance N is related to the number of kilograms of a substance M by its molecular weight M. So I'll just write those three definitions. N equals kilomoles of a substance. M is the number of kilograms, so that's mass. That's a good thing. That didn't change.
Little m or big?
Little m equals the mass of a substance. In kilograms, we're going to measure that in kilograms. And then M, big M, equals the molecular weight. Okay, this is not as bad as it looks. We've got all the tools we need to figure this out. So, what are the molecular weights? I think if we just click on properties. Let's see. Oh, right here. Yeah. So I'm looking at carbon. I've got my mouse over carbon. I can see that it's come over here without hitting something else. It's number 6. That means there's 6 protons in its nucleus. There are 2 electrons in its 2s orbital, and then the 4 in the 2p, like we just said. This number right here is its molecular weight, 12.011. For now, I'm just going to use the number 12. Where's the 011 come from? Well, carbon sometimes can have more than 6 neutrons in its nucleus. So sometimes it's going to have 13, sometimes it's going to have 14. If I'm not mistaken, I think those isotopes might be slightly radioactive. They're not stable. They can decay.
Is it the alternate, like carbon-13 or carbon?
Yeah. And so I'm not familiar with all the physics of how those necessarily get there, but the fact is there's a little bit of carbon-13 and a little bit of carbon-14.
And there's even like a rate that's in there, right?
Yeah, and some of it depends on like when the carbon itself was formed. If you get a chance, go watch some Neil deGrasse Tyson. He talks about all of the carbon on this planet. I mean, it was forged in a supernova, like some giant sun, not just like ours, but a giant sun like ours collapsed. Fused hydrogen into heavier elements. Carbon's one of them, and just kind of randomly when the the subatomic marbles were coming together, there's a few extra neutrons banged in, and they're just stuck inside the nuclei of those old carbons, and they're still kicking around. In general, and I think, yeah. So the amount of I hope I have this right. The amount of carbon-13 and carbon-14 on planet Earth is diminishing, if I'm not mistaken, just from decay. We were talking last time, I think, a little bit about, are the photons immortal or the electrons? Well, the nuclei themselves aren't necessarily immortal. Since carbon-13 and 14 are unstable, they'll decay. It'll still be carbon. You'll still have those 6 protons in there, but it'll decay back down to 13 or 12, etc., until it becomes more stable. Because you can think of that supernova sort of cramming these things together in unstable. So I think that's how carbon dating works. Is in the past there was more 13 and 14, and so when something dies, it's sort of stuck with whatever 13 and 14 was in its body, etc., etc. So anyway, that's kind of the deeper meaning of why we see 12.011 instead of just flat out 12. Okay. So molecular weights. Let's just do it for carbon, and in this case, I'll just write 12 in the basement here. As I said, I've got this nice little bag of carbon. I do not have a scale with me, so I'll just do a little pretend measurement. I'm looking at this thing and I'm thinking, gosh, I don't know. It probably weighs 1/10 of a kilogram, maybe 1/20th of a kilogram. And a kilogram is twice the mass of a pound. So I'll just write that out.
Just a cup of carbon weight.
Yeah. Well, you're talking diamonds or this amorphous or carbon nanotubes. It's yeah. Carbon. I think, and again, take a look at deGrasse Tyson. He talks about how carbon will interact in more ways with more elements than any other element on the periodic table. So I'm just going to say this guy weighs, what did I say? I'll just say 0.05 kilograms. That's the mass. That was my little fake measurement that I did. And so from that, I can have the number of kilomoles. And now I just, what's a kilomole? Well, let's get to that, but let's figure out how many kilomoles we have. I think it's pretty clear where the 12 is coming from. That's the molecular weight. I think it's pretty clear where the 0.5 is coming out. Now we can see what is this N thing. Okay, so 0.05 divided by 12 equals 00. I'll just call it 0042. 0.0042 kilomoles. No, I'll write it over here too. 0042 kilomoles. Okay, so what's a mole? It's a weird number. It's but it's kind of fun. It's
It did the first time.
Yeah.
Oh, man. I was trying to convert pound moles to kilomoles for like 2 hours. I was like, oh, wait a second.
So a mole it's just a number is the funny thing. Where is the thing? Oh, it's right here. So here it is. It's 6.022 times 10 to the 23rd. So it's a pretty big number. And it's how we get from the molecular scale up to the human scale. So what this means, and let's just do another example where we work backwards, and let's just start with the mole. So 6.022 times 10 to the 23rd. So let's just work backwards for a second. 1 mole equals 6.022 times 10 to the 23rd, right? And it's fine, whatever. It's a you can think of it as like a trillion, or a billion, thousand, or there's a lot of different ways to think of it, but it's 10 to the 23rd, 6.02. So, but the nice thing is that big number is just 1 mole. So you don't, for now, we don't really have to, remember that, but you just say that, just like 1 Google is 1 times 10 to the 100th. You want to say 1 times 10 to the 100th, or you want to say 1 Google? Well, let's just say 1 mole in this case. So let's just do the problem backwards, and let's just say I had let's go one step further. 1 kilomole is going to have to equal 6.022 times 10 to the 26th. That's just 1,000 moles, right? Okay. So let's work backwards, and I'm gonna say I have actually 1 mole of carbon. And what does that mean? Well, and let's just pretend. Let's get some get a visual going. If I walked up to you, I said, "Hey, I've got a mole of carbon in this bag." And you're like, "Oh my gosh, is that a lot? Is that a little? How much is it worth?" Well, you got to figure it out because you don't really know what you're buying. It's the same thing like, am I buying an ounce of gold, a pound of gold, a milligram? Again, you have to do the same thing with any other commodity that you're purchasing, bacon, whatever. So I've got a mole of carbon. Well, how much is that? Let's work it backwards now. Actually, let's say I've got 1 kilomole. Make it easier since N is in kilomoles. I've got 1 kilomole of carbon. So let's just say 1 kilomole of carbon, and I know that the molecular weight is 12. So the question is, what does little m equal? Well, now it gets really simple. We just say that in this case, little m equals 1. That's what n equals, because I just told you I have 1 kilomole. 1 k mole carbon times 12 equals 12. What are the units? Well, we already know that they're in kilograms, 12 kilograms. So obviously this little bag that I hear does not weigh 12 kilograms. So you could say, "You're lying to me. I know that's not 24 pounds of carbon in there. I want my money back, or show me the rest of the carbon." So that's how you would run that little negotiation. So, but with bigger production, I could have a full kilomole of carbon, and in fact that would weigh 12 kilograms. Yeah.
So, what do I weigh in moles? Can you do that?
Oh, so what's a human weight in moles?
A human mole.
Yeah. The chemistry gets a little trickier because what you'd have to do, and we'll get there eventually. You have to know is like what fraction of you is hydrogen, what fraction is oxygen, what fraction is carbon. You have to know like what fraction each one is.
Okay. So you can't just take a weight and say it weighs this many moles.
No, you can't. It's the same way. With your car, you could go and weigh your car, but like some of that's glass, some of it's rubber, some of it's steel, et cetera, et cetera.
Moles that was, you have to know what each portion is.
Yeah, so
Okay.
that's a great question. You would know what your weight is. You'd have to know the ratios of each one of those. And then you could say from that, I've got this many moles of oxygen, this many moles of carbon. So, and you would do that in biomass too. In fact, it becomes super important with combustion. It's like, how many moles of sulfur are in that thing, because it's going to combine with something, and what do I have to add to get the sulfur out, et cetera, et cetera. To get the complete reaction. Yep. Good question. Perfect. Okay. So I think in the last 20 minutes or so, I think we have covered chemical mass balance. We did a little bit of stoichiometry with the methane combustion. There's our oxygen, CO2 coming out, water coming out, nitrogen just coming along for the ride. That was equation 2.3. We also went over molarity, which is equation 2.4. There it is. There's only the 3 variables. The molecular weight, we know, we get that right from the periodic table. We rounded carbon down from 12.011 to 12. We're very familiar with what the mass of a substance is. The wild card here, if you will, are the kilomoles. But I think now we've got a handle on what it is, because we worked it forward by saying I started with a 20th of a kilogram of carbon. That was the molecular weight, and that's how many kilomoles I had. Then I lied to you and told you I had a full kilomole of carbon in this bag. Well, we did the math and we determined, well, no, probably not. You probably don't have 12 kilograms. So we did the problem forward and in reverse, so hopefully we can use this equation. Is that good? All right. Yeah, I like that. I like that. Okay, that's pretty cut and dried. I'll take another break, and then we'll do, do you guys have anywhere to be at noon? Are we okay for time? I can go a little bit over.
I can go a little over. We were going to meet a couple people for an AC lab, an early AC lab.
Okay.
But it's not, our class doesn't start till
1,
one.
but we're
Okay.
We're
Well,
trying to go early.
I'll just, I said we'll take in a couple extra minutes here. We'll just take a break, and then, yeah.